reactivity for this. And some of this will be a bit of a review from what we saw in the video yesterday. But to start, let's take a moment, if you would please, and let's predict the product. Remember, let's write this a little bit nicer. Let's take this compound here and react this. I don't think that's nicer, but we'll go with it, with bromine in carbon tetrachloride. So if you want to take a moment, please, let's just go ahead and predict the product for that particular reaction. And if you're really enthusiastic, you can even draw the mechanism. We won't go through entirely the mechanism here, but let's think about what the product is. So I just like it because you can see what's happening.
Okay, see the shadow.
Yeah.
Where's your microphone?
It's in here.
So that's what you were saying.
I was going to get another. If you hear noise in the background, it's just because I'm discussing something here. I was going to get another microphone because you can hear the tapping on here,
Yes, yeah.
but I haven't done that. Yeah. But then I can also see what things.
Yeah, no, whoever tried it with a camera.
No, I haven't.
Who has them?
I think Michael does. So this seems to be a.
Oh, that's to work great. It's following the chat. I think that's great.
And it's automatically saving everything all the time, which is nice.
That's great.
Yeah. Just have to get the chemistry right.
Yeah. Like you, I got some of that.
Oh yeah, I need to get a keyboard. Yeah, that's the.
It's nice to have them.
I can't type on here.
Right. I don't.
Oh, good.
Yeah.
Okay. Hopefully everyone had a chance to see what the product is. Remember, this goes back to the addition reactions. And as I mentioned, we won't go over the mechanism. But remember, this bromine is going to be added across the double bond. We don't have to worry about regiochemistry because on each side there's a bromo substituent. But the stereochemistry is important in that the addition of the bromos are going to be anti to each other. So you'll have this plus, I'll be lazy this one time here, more than once, but plus the enantiomer. The reason for bringing up this reaction is that now let's consider benzene. And in this particular case, it might look at first like we have this triene, 3 alkenes. However, we're going to see the reactivity is quite different, and this is going to be very important. So now, if we were to take benzene in the presence of bromine, and again, carbon tetrachloride is our solvent, we would actually see that there's no reaction. So that means that this benzene is not acting the same as the alkenes that we've seen before. So I remember, right, you had to use all sorts of reactions where you've added different groups of electrophiles to this alkene. However, benzene now seems to be acting much different. However, let's put in one more reaction. Let's take that benzene and draw the same resonance structure. Benzene, let's add bromine and a new reagent. Let's use iron tribromide, which we'll get to later on. Now, indeed, you'd actually see there is a reaction. However, the product is going to be different than what we'd seen from our earlier addition reactions. Instead of adding, say, bromine across the double bond, notice here in the alkene, we added bromine across the double bond and we lost the alkene. We ended up here with this alkane. Now, instead, what we're going to end up doing is we'll just show this hydrogen here. We're substituting this hydrogen with the bromine. And so what's important is this is a substitution reaction. The hydrogen is now replaced with bromine. And then second, we've actually maintained this benzene ring, which will be our aromatic structure. So we need to figure out mechanistically, how can we come up with an explanation for this substitution reaction? And that's going to be a main component that we're dealing with our 5 major reactions. Now, I think because of that lengthy video that was posted yesterday, we'll leave the discussion for the stability of these aromatic compounds and how that's determined with this heat of hydrogenation to the video. So if you have any questions about that after seeing it on the video, just please feel free to ask. But I think in the interest of time, we won't repeat that here. But instead, what we want to do is think about why is benzene here as our sample aromatic compound, why is it so stable? And that's what that heat of hydrogenation showed. So I think to help illustrate that, let's go to a couple of those slides that were on that video from yesterday, and just click this one. So this was about midway through, and we can use this rather than having to draw benzene multiple times and see me scribble writing orbitals. Let's just use these pictures. So as was mentioned earlier by Ryan and James, right, we can actually write this structure for benzene with the circle inside the ring. And the reason for doing that is that these two structures here highlighted as 1 and 2 on the benzene might make it look like you have these alternating single and double bonds. So a single bond here, double bond here. However, that's not the case. One piece of experimental evidence that argues against that is actually all of these carbon-carbon bonds are the same length. If this was a single bond or a double bond, then you'd expect different bond lengths. So one, all bonds are the same length. And then number 2, if you look at that carbon-carbon bond length, it's going to be 1.39 angstroms. We don't need to memorize that number, but what's important is that that number of that bond length, 1.39 angstroms, is in between the bond length of a carbon-carbon single bond and a carbon-carbon double bond connected to an sp2 hybridized carbon. So it seems that they have some double bond character, all of them. And so that's what's shown here, is that these two structures shown as benzene, these are actually resonance structures of each other. So remember, resonance is this concept that's just kind of made up to explain this phenomenon. These structures are not flipping back and forth, but it's all of them at the same time. So one way to write that would be this resonance structure. You can write those arrows that would go to form from resonance structure 1 here to structure 2. And the shortcut then to better illustrate that the electrons are distributed throughout the ring is to put the circle in the ring. Now, when we're discussing our reaction mechanisms, we'll typically draw the double bonds. It doesn't matter if we draw it as 2 or 1. And the reason for doing that is the circle is a great tool, but you lose count of the number of electrons that you're dealing with. And so that's why sometimes we'll end up using this structure. So now to give us a better perspective as to what this structure of benzene looks like, we can use these molecular orbital diagrams shown on the bottom. And that's what I tried to bring in some background with the dienes for what the molecular orbitals represent. And so I think also in the interest of time, we're not going to go through all of that material again that was on the video. But when we're thinking about these benzene, aromatic compounds in benzene here as a representative example, notice it's very electron rich. So we have electrons above and below the plane of the ring, and it's distributed throughout the ring. This can be exemplified by B here, where notice on the top, each of these carbons is sp2 hybridized. So it's going to be forming 3 bonds with the sp2 hybridized orbital. So let's just take this bottom left carbon here and pointing to B here on the bottom. It's forming a bond to the carbon on the right, carbon that's going back, the hydrogen. And then the p orbital is allowed to be used for this pi system of electrons. Every carbon is sp2 hybridized, so that's why we have this ring of electron density above and below the ring in this pi system. So that's going to be important for thinking about this concept of aromaticity. All right, and then I had shown the molecular orbital description of benzene from before, and so let's briefly revisit this. And I know this repeats the video a little bit, but the idea is when considering these molecular orbitals, looking at the electrons that are in the pi system, we have 6 electrons, so we have 6 atomic orbitals, which equals 6 potential molecular orbitals. And that's what's shown here on the right side. And we can arrange these molecular orbitals in arrangements that either form molecular orbitals that are more stable than the individual atomic orbitals, so-called bonding molecular orbitals, or less stable, which would be these anti-bonding molecular orbitals. We're going to see in these compounds that have this high level of resonance stabilization, these aromatic compounds, that we can fill these bonding molecular orbitals, come up with an explanation for their stability. So I know I went through that in a little bit of depth on the video, so we'll leave the video to hopefully describe that. But what we want to primarily think about now is what is this description of aromaticity. So we've been talking here a little bit about, I'm going to go back up for a minute, that these compounds like benzene, and we'll see some others, are aromatic. And so let's think about now how can we actually identify a compound that's aromatic. And that's going to be important later on because it's going to help provide some basis for the reactivity that we're going to talk about. Okay, so let's go back to our notes here for that. And really, you can use this as an example. So if we would have this observation that, okay, this alkene is undergoing this addition reaction, and then we'd say, okay, well, this benzene has no reaction, but it undergoes this substitution reaction. So what's going on? And one explanation might be, oh, this compound is aromatic. So we want to think about what that means. So this was addition. This was no reaction. This was a substitution reaction. So you get most of the letters in there. Okay, so now let's consider a couple of different possibilities when thinking about aromaticity. Sounds strange if you say the word enough times. Aromaticity. Okay. So really, we're going to ask, in some ways this makes me actually think of, it's like we're presenting on a game show, but we're going to ask, is the compound, I'll say not aromatic, aromatic, or anti-aromatic. So we need to define those and see what it means and how it's going to affect the reactivity. So something that's not aromatic are a lot of the compounds that we've seen already. So not aromatic could be something like butane or cyclohexane, for example, or a variety of other compounds. Or it doesn't just have to be an alkane, it can have an alkene, such as this one butene or but1-ene. So these compounds, we'll see in a minute, they don't meet this definition of something that's aromatic. So let's put the definition out there and then see how we can have compounds meet this criteria. So the definition of aromatic. Need to have spell check on this iPad. So a couple of things. The compound needs to be cyclic. And let's put benzene over here and see if it meets this criteria. We've been saying benzene is aromatic. It needs to be cyclic. All right, benzene is cyclic. It needs to be planar. And this is going to allow for the orbital overlap that we'll need for this definition of aromaticity. So we're going to assume benzene is planar. And for a lot of the compounds that we'll look at, we'll first assume that they're planar. It needs to be conjugated. So what this means is that we need to have a continuous orbital overlap of the p orbitals so for our pi system. So every atom has to have we have to have a p orbital available on each carbon. I'm sorry, on each atom. It doesn't have to be carbon. And then last, this is the challenging one at first, is it has to meet this explanation, which is known as Huckel's rule. And this seems abstract at first, but let's put it out there and apply this to a few cases and see if it makes sense. So Huckel's rule states that a compound will be aromatic if the number of electrons in this pi system is equal to 4n plus 2. So this is pretty much the level of math that we're going to see in this class. And so the number of electrons has to meet this 4n plus 2. N can be any integer. So n can equal 0, 1, 2, and so on. Which means the number of pi electrons would have to be something like if n is 0. I don't have my calculator, but I think if n is 0 here, this is going to be 2 in the end. So if we had a system that had 2 pi electrons, that would satisfy the definition of aromaticity with Huckel's rule, as long as it meets these other criteria. So it's best, I think, explained through example. So let's go back to benzene.